Now our section is open. We request all the participants to listen the section from the beginning to end and contribute your discussions and suggestion so that this section will be a wonderful one, remarkable, rememberable one in our knowledge sharing section. And we got an eminent personality for today. As we all know that we all are tired after one day satyagraha, but it will be better to boost up our knowledge with this wonderful section. I would like to our state general secretary and state president uh, Tambi and Santosh Kumar ES are attending this function. It will be an honor for us. And moreover, our aquatic coordinator Joey, Comrade Joey, also attending. I welcome all of you on behalf of AKWA and formally welcoming our speaker and introducing himself. I invite Dr. Renju to kindly do the introduction section and start up our section. Did anybody like to speak in the beginning, like a General Secretary or President would like to share any few words?
No, we can start to the classes onward
Okay.
now itself.
Then we can directly go to the starting section. I welcome Dr. Renju to introduce our speaker and start the section. I'm welcoming all the participants once again to attend to this section.
Thank you, sir. Am I audible? Am I audible, sir?
Yeah.
Yes.
Okay. Sir, my name is Dr. Renju Mohan. I'm the convener of Aquatech. The Association of Kerala Water Officers, they're having several committees are there. This Aquatech is handling the technical aspect of association's work. So just I will introduce our speaker. Today we got an eminent speaker, Dr. Raghuveer Rao, sir. He has been a faculty a member in the Department of Civil Engineering, Indian Institute of Science, Bangalore. He served as a principal research scientist in the Department of Civil Engineering. He has a lot of experience in the field.
Renju, your voice is breaking.
Personally,
Kindly check
I
your
think
audio.
about 5 engineers from Kerala, AKWAO went there and attended in the wide range of specialized areas, including soil investigation and dynamic soil testing, slope stability analysis, foundation design, soil analysis, water supply. Sir, it's audible, right? Am I audible, sir?
Now audible. During your speak, some voice is cutting.
Okay, sir.
Now it's okay. Now you continue.
Okay. So, sir has a lot of experience in surge analysis of water supply mains and liquor irrigation system, transient analysis of cooling water system for thermal and nuclear power plants, and surge analysis for slurry pipelines and crude oil pipelines. In addition to his academic and consultancy contribution, he has trained more than 700 engineers, significantly contributing to the professional capacity building in geotechnical and pipeline engineering domain. As I already told, I am fortunate enough to attend his section. He developed a software called the Surge Analysis Program. We got a hand-on session in that too as well. During for inviting him to this particular session, I contacted him several times, even if in his busy schedule, he attended all my calls and all my WhatsApp message, everything. And very happy to introduce him to this Aqua Technology sharing session. Thank you so much, sir, for attending this session and for the time for spending with us. I welcome sir once again and take class. Thank you so much for the opportunity.
Good evening, everybody. So thank you, Dr. Ranji Mohan, for your nice introduction. Hope all of you can see my screen.
Yes, sir. Yes, sir.
Yeah. Okay, so so when Dr. Ranju Mohan asked, no, first I thought I will talk about search, but I have something very important topics before search. So maybe we'll have one more session on search a little later. Okay. So let me start my presentation on design of pipelines and pumping systems, review of current practices and recommendations. So most of you must be involved in design of pipelines and pumping systems, right?
Yes, sir.
Yeah, and also maybe construction, execution, then maintenance, everywhere you must have been involved, right? Okay.
Yes.
Yeah. So now, yeah. So before starting acknowledgements, I thank late Professor K. Sridharan, my colleague, former colleague, for introducing me to this topic of surge analysis in the year 2000 and associating with me till his demise in 2011. And we together trained and did consultancy till his demise. And I thank all my clients for their confidence in me. And I thank all the participants in the training programs where I also learned from them. And thanks to Dr. Ranju Mohan for this invitation and arranging this lecture. And basically motivation for this talk is I've been involved in this surge analysis for the past 25 years. So I have done surge analysis for more than 400 water supply mains, lift irrigation schemes, micro lift irrigation schemes, circulating water systems for thermal and nuclear power stations, makeup water, ash water recirculation, slurry pumping, crude pumping systems. So all kinds of full range of systems where surge analysis is involved, transient analysis is involved, I have done. I have done a lot of projects both in India and abroad. And we have trained more than 600 to 700 people in these design of pipelines, pumping systems and surge analysis. And I have also reviewed several pipeline designs and surge analysis reports which were done by other consultants. And while doing so, I observed the following major issues. One is the estimation of friction losses in pipelines. There is a lot of uncertainty and several formulas are there. And people are using all kinds of formulas. And I will discuss about that. And another major issue is about determination of pipe wall thickness for large diameter steel pipes. So this is also one big issue where people have a lot of ambiguity and no clarity on this. And most of the times, the state boards and corporations and departments, they say you get the surge analysis done by somebody, some like IISc, IIT, something like that. So we should able to identify when we really need surge analysis. So I want to talk a little about that requirement of surge analysis. So about surge analysis, I will talk in different lecture, but right now I wish to cover these three topics. Okay. So now we will see how to calculate pump head and what are the friction formulae available for us. And CPHO guidelines also we'll discuss. And we'll talk about design of pipelines and design of large diameter steel pipelines, requirements versus codal and manual provisions, and what are our expectations, recommendations, we'll conclude. So basically, whenever you want to design a pumping scheme, so you have source at some level and you need demand at some other level, and which are a distance apart. So we will calculate the pump head required to pump some amount of water there. So that amount of water may be designed based on the population for current stage, and then maybe after 15 years, what is the scenario, how to increase the supply of water, all that will be there. So in doing so, you need to calculate what is called pump head. So this pump head basically consists of static lift, that is the elevation difference between the source and the demand, and friction losses through the pipe. And then we will also has to account for some minor losses because there will be a lot of bends and joints, all those things. For that, we need to account for some minor losses. And then in the pump house also, there will be some losses, so pump house losses. So basically, we calculate pump head as sum of static lift plus friction losses plus minor losses plus pump house losses. So as all of us know this how to calculate, but now major issue is your static lift, if anybody can calculate, it is simply the elevation difference between source and the demand. Whereas friction losses, we have several formulas. So when we go to static lift, again, there is some minor variations here. So how is the outfall arrangement? So if you see the outfall arrangement here on the left side, so water is being discharged at the top of the sump or top of the outfall, whatever it is. So here you can have three types of arrangement. The one here shown here. And other thing is you can have a pipe connected to the bottom of your outfall or sump, and where you have a overflow section. Or sometimes the pipeline may be more than the overflow section. So in all this, in the first case, you will take this as the delivery level. In the second case, you will take this overflow level as the delivery level. In the third case, you will take the top of the pipe as the delivery level. So now from this delivery level minus the minimum water level. In the source, no, you may have varying water level. You can have minimum water level, maximum water level. But our idea is to pump in all the seasons. So we will take the static lift as a difference between the elevation at the discharge minus the minimum water level. Now, once you calculate the static lift, then you need to get the friction losses. So for friction losses, there is one manual on water supply and treatment systems published by Central Public Health and Environmental Engineering Organization. So this is kind of a Bible for most of the state government design departments, what I've noticed is. And fortunately, this has been recently revised in March 2024. Otherwise, it was made in some 1970s. People were using till date. So here we have given some formulae to calculate the friction loss. Like here, the first one is the Darcy-Weisbach formula. So which is in the H is equal to FL V square by 2GD. So where you have the F friction, dimensionless friction factor, and L is the length of the pipe, and V is the velocity through the pipeline, and into divided by 2, G is the acceleration due to gravity, and D is the diameter. So this is the most commonly used formula. And there are the other formula also is given here. This is Colebrook-White formula, which can be used for calculation of friction factor F. So now basically this friction factor is related to surface roughness of the pipe material, the internal pipe surface roughness. So that roughness one can measure, and using the roughness, you can arrive at this friction factor F using this Colebrook formula. Okay. So, and there are some references also for this, how to calculate all this. And there is a table given here, 6.1. I'll just, okay, go to the table a little later. Yeah. So then we have another popular formula, Hazen-Williams formula. So here Hazen-Williams formula is given as V is equal to some constant into C into R to the power of 0.63 and S to the power of 0.54. Where V is the average velocity and C is the Hazen-Williams constant, and R is the hydraulic mean radius, and S is the slope of the hydraulic grade line. So as here it is given in terms of V, but we are using this formula for calculation of friction loss. So then we need to rewrite this formula like this. Here H is equal to 10.68 into Q by C to the power of 1.852 into L by D to the power of 4.87. So here, if you use everything in meters, you will get in head loss also in meters. So the main difference between Darcy-Weisbach formula and this one is here, this is dimensionally correct, whereas this is not dimensionally correct because you have very odd powers here. Okay. So now, though they have given these two formulae, but subsequently in the latest version of CPHO manual, they have given some more guidelines like coefficient of roughness for different pipe materials. So here they say today we should do everything very judiciously and economically. So there is an urgent need to avoid design of the pipe, avoid over design of the pipelines. So they say you evaluate the coefficient of roughness and use this Moody's chart to get that. So, and some more guidelines are, however, for normal ranges of Reynolds number 4000 to 10, the friction factor and C value does depend upon the diameter, velocity, and relative roughness. So this is the guideline given here. And depending on the quality of workmanship during manufacture and manufacturing process, cement mortar, epoxy line metallic pipes tend to be as smooth as PVC, GRP, and other plastic pipes. So earlier we used to put kind of cement mortar internal lining and external gunneting for steel pipes. But nowadays they are mostly going for epoxy lined metallic pipes. So what they claim here is epoxy lining is as smooth as a PVC, as GRP, and other plastic pipes. So, and they also continue to say that metallic pipes lined with cement mortar, epoxy, concrete pipes behave like smooth pipes and have shown C values ranging from 140 to 145 depending upon the diameter and velocity. That's what they give. And then there are so many things. And then finally they say design purpose C values are the same as that of new pipes or lesser. Why? Because earlier they used to give a table where the C value to be considered for the design purpose and for the construction purpose differently. So that's why here they are saying that it is for same for the new or lesser. So here is a table where they say for mild steel, for new pipes you take C140, for design purpose you take 100. Again, this is kind of not a very good situation. During the design purpose, if you use, you will end up with very high pump head. And at the time of implementation, suddenly if you start using C140, what will happen? Your pump head will reduce drastically and all your estimates has to be revised. And they also say projection method for cement mortar and lined metallic pipes. For mild steel pipes, they say use between 130 to 110. So the window of 100 to 140 has reduced to 110 to 130. And they say for large diameter pipes, they can use in the range of 90 to 125 for less than 500 mm. And in the absence of specific data, the values up to 130 may be adopted. Okay. So though they are given this table, but with this notes below, again, there is not so clarity in which C value to be used. And this is about the friction factor. That is, if you want to use Darcy-Weisbach formula. So here they are given diameter from 100 to 2000. You can use from F00 0.01 to 0.02. Okay. So now generally what we do is as per the procedure given here, you are supposed to measure the surface roughness of the pipe material. And then you have to calculate the relative pipe roughness. Okay. So then use this Moody's chart. Here you have Reynolds numbers on the x-axis. On the y-axis, you have one side relative pipe roughness. On the other side, you have friction factor. So though this chart is available to us, but this guideline given here is 0.01 to 0.02 will lead to a C value ranging between 166 to 114. So this margin now is going beyond the margin provided here, either 100 to 140 or 110 to 130. That band is within this band. Now this band is expanding beyond that. Okay. Now, if you really measure the surface roughness, this for a cement mortar lined DI pipe, I measured myself. I procured one surface roughness measurement device and measured. And based on the roughness here in micrometers, I calculated for different velocities what is the Hazen-Williams C, what is the friction factor I calculated here. So if you see, for any range, for any diameter pipes, this is all the time more than 150. So it is more than 155 rather, 155 to 159 I am getting. So can we really use this type of factor is the question. Okay. So now The new manual again continues to say reduction in carrying capacity of pipes with age. It says a decrease in the cross section due to accumulation of deposits in the interiors of the pipes and an increase in the roughness. They say now this slightly contradicts the previous one. So now it says because of this, there is reduction in C value. That's what they say. Okay. And also they say here the Darcy-Weisbach formula is dimensionally consistent. However, its use for the estimation of the velocity discharge during the analysis of the network diameter or in the design of the network is tedious, as the F value cannot be calculated if the velocity or diameter are not known. A repetitive method is required. Initially, if F is assumed and unknown velocity discharge diameter as the case may be calculated, then calculated velocity discharge diameter F is obtained using Colesbrook-White formula. I have shown you these two formula in the previous slide. So from there, you need to calculate by trial and error because F is there on the both sides of the equation. And the obtained value is found to be the same and the process is terminated, else the value obtained is considered and the process is repeated. And again, they continue to say that Hazen-Williams formula is derived for hydraulic mean radius and all that and dimensionally inconsistent. And however, Hazen-Williams coefficient C is usually considered independent of the pipe diameter, velocity of flow and viscosity, unlike your F, Darcy-Weisbach F. Over a century, engineers have been designing millions of kilometers of the pipeline using the Hazen-Williams equation, and those pipes are still in operation today. It is possible to calibrate models using the Hazen-Williams equation to match actual piping systems. Very good. This sentence has been provided, but subsequently they have diluted this sentence by writing these lines that if there is a choice to use pipe friction formulae, Darcy-Weisbach, which yields accurate results, can be preferred over Hazen-Williams formula. However, no other formula for head loss in pressurized pipe flow conditions should be used. Now you see, there is a contrast difference between this line versus this line in the same page, rather same paragraph. So this is a bit ambiguous here. And they say method for determining value of C for the existing pipes at the site. So they wanted to consider a length of 105 meters pipe and put some marks 100 meters apart. And you measure those things, average pressure and average pressure at different place and average discharge you measure. And then you back calculate and using this formula, you evaluate the C, they say. But really, if you have really access to a pumping system existing, working for several years, back calculating C is very simple. You know the minimum water level in operating water level in the sump, you know the discharge elevation, and you know the flow through the pipeline. You can simply back calculate and see what is the C value. This exercise somebody did and found that most of the cases, whether it's a new pipeline or 10 years old, 20 years old, lined, unlined, everything, the back calculated C value ranges from about 130 to 120 to 130 plus 10% minor losses plus some 1 to 2 meters loss in the pump hose. So that is a better estimate than the procedure given in the latest CPHO manual. And similarly, if you want to estimate what are the minor losses at different positions, then usually the formula what we use KV square by 2G. So here some standard values are given for different sudden expansion, contraction, bell mouth, and 90-degree bend T, and different types it is given. So this varies mostly from about 0.1 to up to 5, some places 10, depending upon the type of the fitting and wall. Okay. Yeah. Now in the earlier version of CPHO manual, there was an equation called modified Hazen-Williams formula. So they said that the requirement of this formula is considering that Hazen-Williams formula is non-dimensional. They have come up with this formula. But unfortunately, even this formula also is dimensionally incorrect. So here this is given as instead of C, they are considering a value called as CR. So 143.5 into CR into R to the power of 0.65 and S to the power of 0.55. So if you rewrite like regular Hazen-Williams equation, it comes like this: L into Q by CR to the power of 1.81 divided by 994.62 into d to the power of 4.81. Here again, it is dimensionally incorrect. But if you compare this CR in the modified formula versus C in the regular formula, so C corresponds to 149 CR. So if you consider CR as 1, so C will be 149. And a few departments in different states recommend to use this formula to calculate the pump head in tender conditions. So once they say use this formula for tender condition, now if the contractor estimate this pump head and provides a system, if we don't get that design discharge, then who is responsible? Is the contractor responsible? Is the CPHO responsible? Is department responsible? So that ambiguity is there. So now the recommendation is the reverse calculation of C for the existing and operating old and new schemes indicate a C value ranging between 120 to 130 with 10% minor losses. The reason being, as it is not practical to remove air completely from the pipeline at several local peaks. So if you don't remove the air from all the local peaks, though you are going to provide air walls at a certain frequency and certain locations, it is totally impossible to remove complete air from the system. So whenever there is an air pocket stuck in some position in the pipeline, the area of cross section for the flow decreases. So that will again induce some amount of friction loss like V square by 2G, as there is increase in V due to that reduction in the area of cross section. So that's why, as it is not possible to do this, so now though you get a C value around 140 to 150 by measuring surface roughness, but actual C value realized in cross-country pipelines is between this range. So gets affected due to entrapped air and results in much lower C value than what is considered as per the table given in CPHO manual and other several sources. So hence computation of C or CR value should not be used based on the surface roughness measurements alone. Better to go by the experience by back calculating the seam values from the several systems which are working. And when you want to estimate the head loss in the pump house, generally we tend to use for each valve or expansion bellow or an expansion joint. So if you consider here some kV square by 2G, you will get very small number in the order of 0.1 to 0.05 meters head loss. But all these formula, that kV square by 2G formula, is assuming that you have enough approach length on the upstream and downstream of that particular wall or a expansion belt. But in the pump house, generally what we do is we will pack these everything closely together. So that kV square by 2G type of formula doesn't work. So here we need to assume some lump sum number like 1 meter, 2 meter, depending upon the total pump head, the loss in the pump house. So in the C value, now we have seen in the field people taking from 100 to 150. So power companies, they will take 100, and water supply companies, to achieve the economy, they will go for 150. And people say that you have to use surface roughness values based on C value based on surface roughness measurement, but I have shown you how that does not work. So my experience with extreme cases is CW systems, makeup water systems for thermal power stations and nuclear power stations, they use C value about 100. And water supply schemes, other extreme, they will use between 145 to 150. But based on the measurements, it lies between 120 to 130. So here, the proper location of air walls is very important to achieve proper C value. And residual head and rounding off accounts for the differences in C value. So particularly when they use this modified Hazel-Williams C formula, they will consider residual head at the terminal point. So though they consider theoretically here, practically it is not possible. Practically, whenever the water discharges at some delivery level, so that level itself will be your HGL. You cannot say you can have some residual head unless you put a wall there and throttle it. And the losses in the pump house should be reasonably estimated for covering these dismantling joint, non-return walls, isolation walls, etc. For this, you have to use a lump sum C value. And what happens if you overestimate or underestimate the pump head? So implications for overestimate of the pump head is higher discharge as actual head is lower than the design. And then if you are supplying to a reservoir or canal, it's okay. But if you are supplying to a water treatment plant that has a finite capacity, so this additional discharge, it may not be able to take it. Then you need to throttle in the pump house and reduce the discharge to design discharge. So thus you may waste energy here. That leads to lots of energy. And the implications of underestimate of the pump head. If you underestimate the pump head, your discharge will be lower than what it is supposed to be designed. What is the design discharge? So now these type of things we can estimate using system resistance curve analysis. Once you have a pump characteristics curve from the vendor, and for the number of working pumps, you draw the number of curves, and then you generate a system resistance curve with some reasonable estimate of the friction loss. Then at the point where it cuts that will be your rated point or the operating point. So particularly when you have a number of operating pumps, then you have to design number of pumps for a particular design, for a particular discharge. If you design 4 pumps for your design discharge and operate 3, you will get lower discharge. Operate 5, you will get higher discharge, but it's not pro rata. That depends upon the system resistance curve. And at times, if there are variations in frequency also, there will be discharge variations because the pump characteristic curve given by the vendor is for a particular frequency. If the frequency is either lower or higher than that, you have to draw a line parallel to that. Okay. So is it clear up to this point? If you have any questions, we can discuss here and then go to the next point.
Sir, please complete. Please continue.
Okay. Yeah, sure. Thank you.
Excuse me, sir.
Yeah.
Dr. IGP Tadatil has raised his hands. He has
Yeah.
Yes.
Please.
Sir,
You can unmute and
am I
ask your
audible?
question. Yeah.
Am I audible?
Yeah, you are audible. You can speak.
Sir, first of all, I appreciate your presentation, and I think it's a blessing. It's a blessing for us, the engineers in KWA. And this question is with respect to the C value.
Yeah.
Adopting the C value, a particular or realistic C value. So for example, if we model a, if we model a pumping line, which is having an extension or a length of nearly 1 or 2 kilometers. So mostly in modeling process or a simulation process, we make it a segment-wise simulation. For example, that total length will be divided into various segments and it will be connected. And that algorithm will have a different routing, like gradient compensation or anything like that. Or else you can even have a finite element modeling also. So, so if we each and every segment, if we adopt a higher C value, then the segment-wise simulation will give a lower. It is as good as giving a lower C value for the total length. So that the simulation modeling process will have a, I think, a different approach. For example, if you for a 3 kilometer pumping line as a complete full stretch, if you model as a single piece of pipeline element, we can have a lower 120 or 130 C value. But when we make it a segment wise, different segments which is connected at the nodes, and then simulate, then if we adopt a C value 120 or 130, it will be disastrous because it will give a very low discharge or like that. We need to give a higher C value. So the C value will, depending upon the simulation technique or the physical piecewise segmentation of the total pipeline. It is as good as it is also applicable for the distribution network also. So this is my one opinion. You can. I want to hear from you. Thanks.
Yeah. So basically, what I am talking is with respect to transmission mains only, not with respect to distribution systems. Okay. So a transmission main meaning the diameter is same, and for a long length cross-country pipelines which supplies the water from the source to the city, and subsequently there will be distribution from the within the city. I am not talking about that. So distribution generally consists of diameters ranging from 1000 mm onwards to maybe 200 mm, maybe 100 mm, all that 50 mm like that, right? Distribution. So this, whatever till now I am talking refers to only transmission mains, which are large diameter. Large diameter meaning I am talking about anything ranging from 500 mm to 5 meters diameter. Okay. So I'm talking about that, which are cross-country long length pipelines. What you said is right in case of distribution systems. What you said is right in case of distribution systems. In distribution systems, what happens is there is a scale down of the diameter, and there will be a lot of connections, cross connections and walls. So many instruments will be there on that. So there, what you said is right. There you can go for your Darcy-Weisbach kind of head loss calculation versus this Hazen-Williams. This whatever till now I'm talking is only with respect to transmission mains. Am I clear?
Yes, sir. Actually, I'm talking about the transmission line also. For example, if you have a longer, for example, if you have a very large pipeline, I mean, in the structure, its length is very large. For example, it is having a length of 3 to 4 kilometers like that. If the model is as a single piece, like a 3 or 4 kilometers as a single piece of element, and if you adopt a lower C value, that is as good as making it into piecewise segments. And for each segment, if you take a lower C value, then the total effective loss is a little lower. So if you make a transmission line into different segments, we have to adopt a higher C value for each smaller segments. That is because of the simulation. It depends upon the way of the simulation.
Okay. Now I'll clarify. See, if you see this formula, here it says L. Okay. So now this L is the length of the pipeline. Now, though we consider length of the pipeline as kilometers, now for every pipe there is a finite length. Like now you cast some pipe in the yard and then bring it there and connect it with several pipes you will connect in the field. So the pipeline could be about 8 to 10 meters length. But the node what you are considering in the model is different. You will divide the total pipeline into some lengths, right? That's what you are referring to, right?
I'm referring for the simulation. During simulation, we make it as a segment-wise pieces.
But that simulation you are doing, though you are doing that, but you know the length, total length of the pipeline, you know. As long as the friction is considered, so it's only the L length matters. Now then afterwards, after calculating this head loss for the total length of the pipeline, you consider minor losses for those joints.
Yes. Exactly.
So that way, this should not matter whether you consider length of the pipeline totally or in segments in any formula. You agree?
Yeah, that is theoretically it is correct.
Theoretically, it means practically what it differs. Practically, we are considering 10% minor losses. Yeah.
No, sir, what I mean is if we use a software, simulation technique, we need a software. In most of the modern softwares, they use a finite element combination.
Finite element method is only to get pipe stress analysis, which none of our hydraulic engineers do. That pipe stress analysis has to be done for process piping in the industries like chemical industry and then your oil industry. There they will do it.
No,
mechanics. Pipe stress analysis, right?
Sir, that is mechanics. I'm talking about the computational fluid flow. Or for example, we can have a finite volume of flow, or else we can leave it. We make it a segment wise, and if we apply gradient compensation or any other technique for a software, because thousands of kilometers of pipeline, it is very difficult to make a hand commutation. So in that way, the C value, if you take a lower C value, we'll get a wrong result.
Excuse me, sir.
Yeah.
Sir, Shaiju sir, please cooperate. We have to complete the section. And if you have a detailed discussion, we can have it at end of this section. And if you have a special doubts, we can message to sir and we will pass to that. And we will have. Otherwise, our entire program will be disturbed. Kindly cooperate, please.
So now we will discuss about the pipes. There are types of pipes. So this which type pipe material has to be used depends upon the internal and external pressure and whether it can withstand maximum pressure and at the same time it's not collapsed by buckling. And if you use any metallic pipe, then we have to see whether is it going to corrode. If it is going to corrode, we need to provide internal lining, external gunneting, and these days mostly paint-based coatings are used. And depending upon the size, we'll select the material. So the popular pipes available in the market are ductile iron DI and mild steel, and then glass fiber reinforced plastic pipe, and then pre-stressed concrete pipes. So this ductile iron and glass reinforced pipe and pre-stressed pipes, these are all manufactured in the factory, and they will be having some particular pressure rating. So accordingly, we will select. But only in case of mild steel, which need to be fabricated in the field. Of course, in the field also, they'll start a casting yard and then do it. So there are certain uncertainties which we will discuss now. So before discussing about pipes, the terminology normally used is working pressure. That means minimum under normal operating condition, and maximum pressure. So maximum pressure is while any surge condition. During surge condition, it will undergo maximum pressure. And design pressure is pressure for which the pipe is designed. And field test pressure, after installation of the pipe, you are going to test the pipes in the field. Certain length of the pipe you will test. So the maximum pressure at the test field is called field test pressure. And some pipes we will test in the factory itself. They are called as shop or factory test pressure. So that is a maximum pressure tested at the factory. Generally, at times they will use either one pipe or two pipes and test. So in case of DI, now this is made from spheroidal graphite iron by adding magnesium during casting, and it has very high tensile and yield strength in the order of 420 to 300 MPa, and it will usually have socket and spygard joints, flange joints, and so there is no welding here. And all the details for this pipe is as per the 8329-2000 reaffirmed in 2020 IS code, and you have a American code, American Water Works Association C150. So these pipes are designed based on internal pressure. So we have different pressure classes here, K7, K8, K9, K10 like that. And these pipes are available from 80 mm to 200 mm. And these will have thickness based on this formula. So normally the minimum thickness is 5 mm for K7 and 6 mm for K8. And we have a nice table here in 8329 Annex E, table 1. So here it is clearly given based on the per each diameter what is the allowable operating pressure for particular K class, and allowable maximum operating pressure, and allowable site test pressure. So it is very simple. If your working pressure is in the order of 80 meters, so if you want to select a pipe, 1000 mm diameter pipe, so you will select K7. K7, so it is 1 MPa. So that is equivalent to about 101 meter water column. So as our pump head required internal pressure is 8 kg, so you have a margin of 20%. So when it comes to such, it can go up to 1.5 times. So here you have a nice table. So using this table, you can appropriately select the pipe, and there is no ambiguity here. But when it comes to MS pipe, so this can be used for any diameter, and this is a homogeneous and strong elastic weldable pipes. So for corrosion, you need to provide internal lining and coating. And this pipe can be casted for any size and pressure. So spiral welding, IS, we have 3 codes here. One is IS 1916, steel cylinder pipes with concrete lining and coating, which covers from 200 to 5000 mm. And we have IS 3589, which covers from 168.3 to 2540, steel pipes for water and sewage. And we have another code 5822, code of practice for laying electrically welded steel pipes for water supply. And in addition to these 3 codes, we have a code which gives the grades of steel, IS 2062. So now if you go to the first code, IS 1916, it says steel cylinder pipes with concrete lining and coating. So this is not applicable for pipe without lining and coating. So here they are given different classes, and this diameters available is from 200 to 5000 mm. So here they have given a table. So this table says minimum thickness of plates for steel cylinders. So here, for example, if you see, you have 1000 mm 6 mm thickness, and 2000 mm 10 mm thickness. So proportionally it is not increasing, you see. And for 3000 mm it is 14, As the diameter increase, the thickness is reducing, nominal thickness is reducing. For 5, it is 24. So if you go by minimum thickness to withstand full vacuum, as per AWWA M11 formula, you need 6 mm for every 1000 mm. So here this first 1000 mm 6 and 6 is matching. So giving a D/T ratio of 167. And for the 2000 mm, instead of 12, it is 10. And for 3000 mm, instead of 18, it is only 14. And instead of 24, it's only 19. And instead of 30, it is only 24. As you see, the D/T ratio is initially increasing, then decreasing. Okay. So now this minimum thickness, if you take, it cannot withstand full vacuum. And there are some details about what should be the pressure for hydrostatic test and how to conduct is there. And there is a provision here in this for minimum thickness of lining and coating for the prevention of corrosion. So here they say it should start from minimum thickness 6 mm to 13 mm. And for lining and for coating, uniformly it says 25 mm. Now the next code is 3589, which is developed in 2001 but reaffirmed in 2022. So here they also give grades of the steels. So steel grades here it is Fe410 and their corresponding yield stress also given. So yield stress for Fe410, which normally we use, is 235 MPa. So roughly about 2350 kg per centimeter square. So in future we'll comparison for that we'll use this. But if you want higher grade, next available higher grade is Fe450. For that yield stress is 275. And what should the pressure for hydraulic pressure test is given here. So P is the hydraulic test pressure given in terms of 2 into ST/D. So this is nothing but rewritten hoop stress formula, PD by 2T. But here they say yes should be 60% of the specified minimum yield stress. So the maximum test pressure to be limited to 5 MPa, whichever is applicable. So here they are specifying that 60% of the yield stress and the hydraulic test pressure shall be applied for 5 seconds. So 5 seconds you will test for this pressure and check. Now this code also gives a preferred dimensions mass per meter length of the pipes. Okay. So here if you see for each diameter there are 3 thicknesses given. So now for the 1000 mm, the minimum thickness provided is 8.8, 10, 20. Okay, for 2000 it is 16, 17.5, 20. For 2500 it is 20, 22, 25. So these thicknesses are much higher when compared to your 1916. So this cannot be simply used. Now recently they made an amendment for this, and amendment number 7 in December 2024, where they say preferred outside diameter and minimum thickness and mass per length they are given. Now even this formula, this table if you see, for 1000 mm, though the minimum thickness required is 6 with respect to collapse, the minimum thickness provided is 7.6, and for 2000 mm it is given as 12, and 2500 it has given as 15. So if you see this, now if you want to use this even minimum thickness of as per 3589, so if you equate that, considering that we will use for working pressure only 50% of the yield stress, okay, assuming that it is 2400 kg per centimeter square for Fe415. So the back calculated P refers to about 182.4 meter water column. So if the pump head is less than this, are we really going to use this thickness is the question. When we have a minimum thickness 6, why we are going to use this further minimum thickness of 7.6? Okay, and even if you use that 7.6, okay, it goes to 182 meter, and then even if you use the 6, it is going to 144 meter water column. But most of our pipeline pump head may be internal pressure may be about 60 to 70 to 80 to 90 to 100 meter water column. Then obviously we cannot provide this thickness, though it is mentioned here as minimum. That's what I want to tell you. Now there is another code, IS 5822, where this says code of practice for laying. So code of practice for laying usually should give about how to lay the pipeline for different terrain conditions and what type of bed socket has to be provided. All that should be given. All those details are provided. But still, after all that, at the end, there is an annex. There they say general requirement for design of steel pipes. Here they discuss about internal pressure, protective devices, external pressure, and also give a provisions for how to calculate the nominal thickness is given here. So to calculate 3, it is PD by some formula is given, where by providing factors for working pressure, test pressure, and if for the field joint and the shop joint, some factors are given. And they say after that, nominal thickness arrived at is subjected to minimum thickness and manufacturing tolerances given in 358. See, you give some formula here and then suddenly refer to another code where some other considerations are given. So again, this gives ambiguity for the people to use. And it says external internal coatings lining should be used in accordance with the code, but shall not be considered add to the strength of such pipeline. So if you have provided lining and thickness, they say it is not for strength of the pipeline, it's only for corrosion protection. And the specified minimum yield stress should be as per 2062 that you can use. And the minimum nominal pipe wall thickness, it says based on the considerations like handling and all. So that handling formulas I'll show you, the handling thickness will be much lower than any of these. So that will not be a criteria. Obviously, this is going to be the criteria. And there are other things like corrosion allowance, how much has to be provided as per something, and then temperature. If the pipe is above ground, what should be the temperature correction to be made, and either you provide expansion joints or provide loops, etc. Expansion joints, loops. And particularly when you have a pipe above the ground, it will be on the supports, then there will be expansion there. Then how to constrain the supports, such details are given here. And another main source available for us is for large diameter steel pipes is AWWA M level manual. Now here it says that the shell thickness should be based on the following, such that worst combination of external loads and where internal pressure atmospheric or subatmospheric radial deflection shall be with or without supporting of the soil and within the safe prescribed limits, it says. Then compressive stress shall be under of the shell under loading conditions 1 above, well below the level of stress causing failure by plastic flow or elastic failure with adequate factor of safety, and tensile stress in the shell under maximum internal pressure and minimum permanent external load is within the prescribed limit of the allowable stress. See, for the pipe, generally what we consider is hoop stress. Hoop stress is effect of internal pressure. So where the internal pressure is uniformly upright around the circumference of the pipe. Now this compressive and tensile stress will be there in the pipe only when it is above ground and kept on the pedestals. But when it is buried in the ground, as there is support throughout the pipeline, there is nothing called compressive stress and tensile stress, but somehow IWWA code gives this. And these permissible stresses related to yield stress and weld efficiency. So working stress for combined bending and direct tensile stress should not exceed 60% of the yield stress. And for working pressure, 50% they say here. And it's necessary to check the shell thickness for adequate factor of safety against failure by buckling and allowable compressive stress, and should not exceed 30% of the yield stress. So though these limits are given, but this code does not clearly provide how to calculate that. And the yield efficiency factor should be 80% for shop, and field is 80% and the shop is 90%. So though this shop weldings are made in the shop in the factory, but obviously the length of the pipe is limited and all these pipes has to be finally jointed in the field. So when you consider in the field, it is only 80% of the joint, 80% efficiency of the joint. And as for the loads are concerned, you have the fill load depending upon the type of the trench condition, and concentrated and uniformly distributed surcharge. That is the effect of the surcharge, overburden soil, as well as the load coming above that in the form of traffic or other things. So these are the loads to be considered. And what should be the maximum deflection? Some limiting values are given here. So if it is only mortar lined and coated, 2% of the pipe diameter. If it is mortar lined and flexible coated, 3%, and flexible lined and flexible coated, 5%. So now there are various percentages, 2 to 5% limiting values of deflection. So you need to check this deflection and ensure that it is within that for the corresponding lining. And compressive stress, maximum compressive stress of the combined effect due to vertical loads, direct hook stress due to external radial loads. So mostly based on formulas given by Spangler, Morley, and Stephenson. And tensile stress, maximum tensile stress under combined effect of minimum permanent load and maximum internal pressure. So you have two types of situation. One is when the pipeline is subjected to subatmospheric pressure or vacuum and external load. That is one condition. And other condition is minimum permanent load and then maximum internal pressure. So for these two conditions, you need to check as per IWW M11. Now we have a code by American Water Works Association. Now I'll show you the distinct difference between this code versus our Indian codes. So here they have given formula for determination of minimum pipe wall thickness based on internal pressure for maximum design pressure and surge or water hammer pressure, and external pressure. Then physical loading, whether it's on saddle support or ring girders, and practical requirements and coatings and linings. So here they have clearly given formulas for each of these. What should be the thing for internal pressure, what should be the for transient pressure and external loads. So actually an approach of this type is better, where we can really make use of the pipe strength to the maximum extent, unlike the tables and charts provided in Indian codes. So here thickness is based on that your hoop stress formula PD by 2T rewritten as, where S is the allowable design stress. So what should be this allowable design stress is very important here. So here they say allowable design stress equal to 50% of the steel specified minimum yield stress for working pressure, and for surge 75%. So this is very clear, and here we can optimize a lot because there is no table and any chart here. And as far as the collapse is considered, they have given the formula, this one, this is a Timoshenko based formula. So here you consider the elastic properties of the pipe, and you have consideration for the lining and coating also. But latest 5th edition of the AWWM 11, so they are not considering this. So only considering the shell alone, considering these as the protection measure only, not for collapse. So we get a formula like this: PC is equal to, by substituting the modulus velocity of steel and Poisson's ratio, you will get an equation like this, some big number into T by D cube. So this formula gives that you need 6 mm for every 1000 mm diameter. And there is another formula considering variations in thickness and out of roundness and manufacturing tolerances. So we have another formula where you have higher thickness of 6.6 mm for every 1000 mm. So as far as the pipeline is buried, then you have passive resistance from the soil. So this formula you can use, but if it is above ground, you may think of considering this formula. And if you see the minimum wall thickness, very clearly it's given T is equal to D by 288 for up to 1350 and D plus 20 by 400 for 1350. And if there is a lining and coating, you can go for this formula D by 240. But in any cases, all these thicknesses calculated for this handling will be much lower than what we normally practice. And external loads, you have backfill, live and impact loads. And the deflection determination is similar to what is given in Indian code. And it says good practice is to use 50% of the specified minimum yields for working pressure and 75 for transient or field surge condition. So instead of 75, maybe you can go up to 60 to 66%. That is 2/3. Like what we consider in our conventional RCC design. So, but now having involved in several hundreds of pumping stations, now I have a table here where in which year, for what diameter, what thickness is provided, and what is the minimum thickness required for withstanding full vacuum, and the corresponding head is given, and I have calculated the hoop stress. So this hoop stress for working pressure, if you compare with respect to 50% of the yield stress, assuming that Fe415 has 2400 kg per centimeter square, half of that, 50% of that is 1200. So if you consider with 1200, you see you already have a factor of safety of 2 to 3 to 4, already it is there. Okay, for the thickness considered here. See, there is you have to strike a balance between providing thickness suitable for collapse condition, for maximum internal pressure at working condition, and maximum surge pressure. But if you have to design for that, then your thickness will go very high, and for cross-country pipelines, even half mm thickness will be costing several tens of lakhs of rupees. So alternatively, you can go for surge protection devices. So you need to see where you have to strike a balance. So if you see all this, though if I see from 2008 to 2024, still our thicknesses are very high in relation to the actual thickness required. Meaning we are simply wasting the steel in the ground. Instead of one project, at times you may have 2 projects, or instead of 4 projects, you can have 6 projects, something like that. So here we should be very discreet about the thickness we consider. And most of the times when the pipeline length is very long, you can go for telescopic thickness. You start with higher thickness near the pump house because you have very high working pressure. As you go along, your working pressure will reduce. You can reduce the thickness. See here, these are very few projects where the thickness is reduced telescopically. So even in 2024, for 2450 mm diameter, just for 172 meters of head, the thickness hoop stress is only 843. Here we could have gone up to 1100, close to 1200 we could have gone by reducing the thickness. You see 25 mm thickness for 2450 mm diameter. D by T ratio is just 100. Is such a waste of steel is justified? Please think and design accordingly. See here 2000 mm, 20 mm. Even with 163 head, hoop stress is only 800, 700, 600. We could have easily reduced this thickness and gone for up to close to 1000 at least. In case of GRP pipes, these are very good pipes and very lightweight and very strong pipes. But only thing is, for these pipes, in addition to internal pressure class, you will also have stiffness class, which determines the collapse pressure for that. But for this pipe, the laying conditions are very strict, unlike the pipes like DI, GRP, and DI and MS pipe and PSC pipes. So here the laying conditions are very strict, which Indian contractors are unable to manage, and many places these pipes have failed because of the wrong placement. Placement is very important in this case. So need for a comprehensive code manual based on the principles of engineering mechanics for easy understanding and design by even at the entry level of less experienced engineers, and less cross references, less ambiguity is required. Now you have seen we have 3 codes and there is a lot of cross references in between. So I expect CPHUO, BAS, IWW, and state boards and departments, corporations should work together in this task in consultation with academicians and practitioners and come with a very good design manual or code so that anybody can use. Like how we have IS 456, any engineer, if you use concrete design or steel design IS 800, everybody will end up with the same design because there is no ambiguities there. There the load factors and safety factors are very clearly defined. Here it is not so. So this is my expectation. So here can you see a pipe failed? So pipes can be generally failed by 2 ways. Okay.
Sir, thank you.
Yeah.
Sir, once again, we thank you for your very good enlightening presentation today.
Yeah.
And we got some of the better practices we
Yeah.
should follow in the field to
Yes.
ensure better life, the design and a better life of pipeline.
Yes.
So I think all of you got what are the best system we should adopt, what are the best practices mentioned in our CPHO manual, BAS and IWWA and state. You taken a earnest effort to present all these things, and we have the time. Actually, we plan to schedule it, close the section within the 9 o'clock, but it
Yeah.
crossed because we started 10 minutes late.
Late. Late. Yes.
Okay, but you finished it on time,
Yeah.
and I would like to know anybody would like to raise any few questions. It will be better, and I request all of you to ask the question. Be specific. Don't
Yeah.
be will be elaborative because
Yes.
we don't have much time,
Yeah.
and I also request our Honorable General Secretary and State President to express their experiences about this section also. First, I would like to ask anybody have any questions? Anybody raise their hands, please no.
Yeah.
Pradeep
Pradeep
Chandra
Chandra.
has raised their hands.
Yeah. You can unmute and talk.
Anyone
Sir,
else?
thank you very much. Can I?
Okay, Pradeep, sure, okay.
Sir, thank you very much. It's been honor and privilege to listen to you. It's a honor.
Yeah.
Thank you very much for that. Since you discussed most about the transmission lines, but I have something related to the distribution lines, which we are normally doing. I needed some kind of advice. I'm requesting that.
Yeah.
Most of our distribution lines, which are connected with the taps, which are exposed to atmosphere. So it's like a line which is connected, a lot of lines connected to atmosphere. So while designing these things, any change in this formulas which is required or something like that, I just would like to know. I
Yeah.
hope you understood this.
Yeah, I understood. But the only thing is that distribution mechanism is entirely different. Most of the times your distribution systems are by gravity, right? You have an elevated service reservoir and then
Yes.
you connect a number of lines, right? Yeah.
Yes.
So there, these type of estimations are not valid. But one thing is based on your experience, you can provide some pressure measuring devices at certain junctions or certain lengths. And then based on that experience, you can rework. That much I can tell you because I am not working on distribution systems. Yeah.
Okay, sir. Thank you. Thank you.
Okay.
Anybody else? Okay, somebody also. No, okay. So now the section, shall we proceed for closing section?
Okay.
Okay, I would like to speak our General Secretary first and then State President. And after that, a formal vote of thanks from our important.
Yeah, some Anup wanted to ask something.
Yeah, somebody else?
Anup? Yeah.
Anup CA can ask. Anup,
Please unmute
Yeah,
and
sir.
ask.
Anup, please.
Hello, sir.
Yeah,
Yeah.
you
Am
are
I
audible.
audible?
Yeah, you are audible. Please speak.
Sir, it was very lucky to have you in this class, sir. It was the class was very good. Sir, I have one doubt.
Yeah.
Regarding the corrosion characteristics while we are reducing the thickness. Is there any
Corrosion?
protective? Sir, you are telling that you are optimizing the thickness of steel pipes while using in big projects and all. So how will it affect the protective coatings or corrosion resistance? How will it affect?
Yeah. See, earlier the codes used to mention that you had to account for corrosion some thickness, right? So, but that thickness,
Yes, sir.
that is only if you are not providing any corrosion protection. See, now there are two types of corrosion protections. One is that concrete based, other is the epoxy based, right? So in case of concrete
Yes,
based
sir.
thing, now there are two different types of pipeline systems. One is for irrigation, which runs only 4 months in a year. Other is the water supply scheme, which runs throughout the year, right?
Yes,
So
sir.
in the water supply schemes, as the water being pumped throughout the year, so there is no problem. You will ensure that all the time pipe is full of water, so the corrosion will be minimum. Okay, so that way
Okay.
you have an advantage. And in case of this epoxy based system, they are very good and they are very effective. So that is also, it is free from corrosion. Okay, so now you need not provide any additional thickness for that against corrosion for these type of systems, but only in case of this irrigation systems where they run only few months in a year, it is very difficult to maintain full of water in the pipeline. Okay, so there
Yes,
you
sir.
have to be a bit cautious in terms of these corrosion thickness for corrosion protection, that you have to account for that.
Okay, sir. Okay. Okay. Thank you, sir. Thank you very much.
Thank you.
Okay, I would like to express a few words by our State General Secretary, Sri Thambi S.
Sir, we are very happy. Actually, this section is an eye-opener section for our management who are forcing to continue the present operation with the very old cast iron pipes and AC pipes.
Yeah.
Because of lack
They
of
need
capital,
replacement. Yeah,
because
they
of
need
lack of
replacement. Yes. Yeah.
capital investments to replace
Yes.
the old age pipes.
Mm.
Actually, what you said here is a
Mm.
scientific way
Mm.
how to face our economic stability to
Mm.
maintain properly.
Yes.
We are having an pipeline water supply system having almost 100 years over. Now
Mm.
still we are going to be run it.
Mm.
We are spending actually 500 crores for
Mm.
power charges and O&M expenses for the same to maintain.
Mm.
Because of we are less shortage of 50 crore for replace it. This is
Oh,
our
okay.
main problem.
Mm.
Actually, our engineering system is maintained by the administrators. Those who are having such type of lack of this knowledge
Mm.
is creating more problem for
Mm.
not only the water supply system, the entire government mechanism also.
Yes.
So those people who are having capacity to advise,
Mm.
actually these people, the scientific field, we have to come forward to introduce this technology in the implementing stage of
Yeah.
running the government mechanism.
Mm.
Whatever we learned in our books must be
Mm.
practiced in our field. That will
Yes.
be we can manage. Then only the every entire system can run economically successfully.
Yes.
So very thanks whatever you did here.
Mm.
Almost all the people who are attended this class is it will be very worthful. Thanks once more. Thank you for sir.
Thank you.
Hello,
Yeah.
Santosh sir.
Yes, yes. Sir, my name is Santosh Kumar. I am actually working as executive engineer,
Okay.
and I am the president of this organization. And I am once again expressing our sincere thanks for spending some time. I know you have going through a very busy schedule in your profession. Anyhow, it was very nice to hear a few words from you. We expect we'll have another session on some other topic which will be related to the water supply sector. Actually, in Kerala, we have a pipe policy, and in the pipe policy, we don't have some specified norms regarding this MS pipe and all these things. Now, Kerala Water Authority has going through adopting MS pipe instead of DI pipes, the bigger dia pipelines, and I think this surge arresting and surge arrestor system is very relevant in such large dia pipelines. Anyhow, The session was very useful for the engineers, especially the officers of Kerala Water Authority. And once again, sincerely thanking on behalf of our organization and on behalf of the entire engineering fraternity of Kerala Water Authority. Thank you, sir.
Thank you.